Hi, welcome back. This is Knowledge Quest 2, and we're going to talk about gear, trains, torque, and power. So what to focus on? How to calculate train values based on number of teeth, why train value is significant, so what does it actually tell you, and how to specify the number of teeth on meshing gears that is required to provide a certain speed increase or reduction, and with that, a torque increase or reduction. This first video presents a lot of the fundamental topics related to speed, torque, and power in mechanical gear systems. We'll talk about these concepts in a lot of detail throughout the class, but this is a good starting point.
Gears. You'll find them in your engines, in your transmissions, in your shop tools, in your toys. They're located in your garage, your shed, even your kitchen. But perhaps most importantly, you'll find them in your bicycles. Always remember, especially when driving your Prius, that the bicycle is the most efficient form of transportation that we have, fueled by simple things like Taco Bell and Mountain Dew. But anyway, let's learn physics. The basics, the most basics of gears, mechanical advantage, what's a torque multiplier, what's a speed multiplier. Two simple meshed gears. If the big one is the input driven by my hand and the small one is the output, this is clearly a speed multiplier because the output is moving faster than the input. Switch it up. The drive gear is the small one. The driven gear is the big one. It's moving slower, so this machine multiplies torque. When analyzing gears, first, just play with the system. Then, clearly identify which is the input, often called the drive, and which is the output, often called the driven. We'll need to calculate a ratio, and you can use either radius to radius, diameter to diameter, circumference to circumference, or, often very conveniently, the number of teeth to the number of teeth, because teeth represent circumference. So 36 teeth to 12 teeth, that little one is spinning 3 times as fast, 36 over 12. That's a mechanical advantage of 1/3. Here's a 36-tooth, 24-tooth combination, which means that the little one is spinning 1.5 times as fast, and the mechanical advantage is 2/3. Remember that any mechanical advantage less than 1 is a speed multiplier, and a mechanical advantage greater than 1 in these cases is a torque multiplier. Note also the change in direction. If one turns clockwise, the other one turns counterclockwise, always with these enmeshed gears. Switch the input and the output, and you now have a speed divider. But more importantly, because it divides speed, it multiplies torque. So the output torque is going to be larger than the input torque. Mechanical advantage in this case, 36 over 24, 1.5. Now we're back to that 36-12 combination. Switch the input and the output, and you now have a torque multiplier. Clearly a speed divider identified visually, so it is a torque multiplier of 3. The mechanical advantage is 3. Note that a counterclockwise input gives you a clockwise output. It is still switching directions. So what do you do if you want to have them both spin in the same direction? One option is putting what we call an idler gear in between the two. You can see that both the input and the output are spinning clockwise, and the two shafts are now separated a larger distance. Now let's talk mechanical advantage and calculations. Watch the number of turns. Output turns 1, output turns 2, and output turns 3. We know that that's a speed multiplier. It's a torque divider. The mechanical advantage has to be less than 1, so it is 1/3. To get that value, the equation turns out to be the driven over the drive, the output over the input. And again, you can use circumference or diameter or the number of teeth or radius. And that idler gear, crazy thing. Doesn't even matter what size it is, because if you watch the output travels 1 rotation, output travels 2 rotations, output travels 3 rotations for 1 input, just as what we had before. Mechanical advantage equation is driven over drive. We'll be using the number of teeth. So 12 teeth, 24 teeth, and 36 teeth is what we have. So that 3-gear combination is 12 over 24 and then 24 over 36. The 24s end up canceling out. That middle gear size does not matter. The idler size does not matter. Another example. This one is a torque multiplier because it's a speed divider. And it takes 1.5 turns input for 1 turn of the output. So the mechanical advantage is 1.5 or 3/2 or 1.5. In addition to using an idler gear, there's another method we can use to make sure that the input and output are spinning in the same direction, and that is use a belt drive or a chain drive. Not only do the pulleys turn in the same direction, the system, compared to the idler pulley system, tends to be lighter, and you can place those shafts any distance apart as long as you have the proper length chain. Now let's find the mechanical advantage. First, you determine by looking at it whether or not it's a speed displacement multiplier or a force multiplier. Output is spinning faster, must be a speed multiplier. Therefore, the mechanical advantage is less than 1. Then you spin and spin and spin and count the number of rotations. The input spins 11, output spins 14. Therefore, the mechanical advantage being less than 1 must be 11 over 14. In decimal form, that's about 0.79. Switch them, you get a torque multiplier, 14 over 11, or 1.27. One final example. This is called a worm gear, usually used for lifting heavy things. Just count input versus output. 1, 2, 3, and just keep on going. Notice that this definitely does divide speed. Therefore, being a speed divider, it is a torque multiplier. And if you counted all those, you get 20. Mechanical advantage is 20. So absent friction, that machine would take your puny little input torque and multiply by 20. Gears, the basics. You just learned physics.
Once you watch the video, now we can dive into gear trains. So a gear train is a series of meshing gears. Gear trains are used everywhere in mechanical systems, and they're used to transfer power through the system. Your power source might be a motor, an engine, it could be you pedaling a bike, or even the spinning blades of a wind turbine. In mechanical systems, we are interested in moving power from its source to power various components. So train value, denoted as little e, is really just helping us relate the input and output speeds. So L stands for last gear in the train, and F is the first gear. You can also calculate train value by the gear teeth number directly. So it's the product of the driving tooth numbers divided by the product of the driven tooth numbers. And note that since the number of gear teeth is directly related to the size of a gear, the pitch diameters can be used in place of tooth numbers to calculate E. Let's say, so we'll start with a bigger gear rotating at 1500 RPM. Driving a pinion, remember the pinion is a smaller gear, at 3000 RPM. So what's the train value here? So it's the speed of the last gear divided by the speed of the first gear. In this case, we don't have a long gear train. We just have 2 gears, so pretty easy to identify the first and last gear. So the last gear is at 3000 RPM. The first gear, 1500 RPM. So that gives us a train value of 2. And really what that's saying is that the last gear is spinning at twice the rate of the first gear. Okay, let's switch. And say the pinion is first and the gear is second. So keeping the speeds the same. Train value is calculated in the exact same way. 1500 over 3000, 0.5. So again, it makes sense. For every 1 full rotation of the pinion, we're only going to get a half rotation of the gear because of that size difference. So that's really what train value is telling you. All right, so this is a more realistic and complex gear train here. So your task for the quiz is to study this figure and determine the number of gears, how gears 4 and 5 are connected, which gear is an idler, that term is defined in the video, which gears are drivers, and which gears are driven. To answer these questions, you'd have to know what side is the input. We'll say this left side, so here's our input shaft, and then output shaft. Alright, so here's a better three-dimensional picture of a gear train. Notice how this first stage here uses helical gears, and the second stage uses spur gears. This is permissible in design, but of course helical gears only mesh with helical gears, and spur gears with spur gears. So a question for you, is this a speed increaser or a speed decreaser? A torque increaser or a torque decreaser? Well, it depends on which shaft is the input and which shaft is the output. So the terminology, what we would call this is a compound, reverted, two-stage, speed, and then we're going to fill in the blank. So let's say that this is our input shaft, our output shaft. This we call the counter shaft, also called the intermediate shaft. So I'll probably flip-flop between those terms just so you get used to hearing them both. But if we say this is the in and this is the out, we can definitely fill in the blank here. So we're going from a pinion to a gear, which is going to slow down the rate of speed of the counter shaft compared to the input shaft. And then again, we're going from a small pinion to a bigger gear, so we're going to slow the rate of rotation even more. So this is a speed reducer. All right, and let's talk about what that means for torque. So power equals torque times speed. And we usually assume that, in most cases, because you have this one power source, that power is constant. There are going to be efficiency losses, heat, and friction. Gears are pretty efficient. We usually assume like 95% of power is transferred through. So if we have power essentially constant, torque and speed are going to vary. So in this situation here, with the left side as our input, the speed is slowing down, and hence the system is going to increase in torque, the torque output. So this is a speed reducer and a torque increaser. And I just want to pause here and say that this is by far one of the most seemingly difficult concepts for students in the beginning, and I totally get it. So ask me if you want more clarification. I can explain it in different ways. But once you see it, once it clicks, it's not something you'll soon forget. So I guess that's good. And again, this isn't like a, super crazy equation. It's just something that you come to know. You'll see it in other classes. Torque times speed, the product that is power. Okay, so when torque increases, speed decreases, and vice versa.
So now let's say the left shaft is the output and the right shaft is the input.
So we have the gear that's going to cause the pinion to rotate more quickly. So this counter shaft is going to be rotating more quickly than the input shaft. And hence the output shaft is going to be rotating even more quickly. So if we switch it, we have a speed increaser and a torque reducer. Okay. So let's take this a little bit further. Erase some stuff. Let's say that the helical pinion here has 20 teeth. Remember, capital N is for gear teeth. And it's meshed with the helical gear that has 80 teeth. And the spur gear over here has 72 teeth. And it's meshed with the pinion that has 16 teeth. All right, so if the right shaft were the input, let's see what we would get in terms of the speed increase. So we're saying 1,000 RPM. So in this first stage, take 1,000 RPM and we multiply it by this ratio 72 over 16. And this is 4.5. So 4,500 RPM. Right, in the second stage, we have 4,500 RPM. That's now the speed of this intermediate shaft. And we multiply it by the tooth ratio. So 4,500 times 4, 18,000, sorry. That's really fast. 18,000 RPM would be the speed of the output shaft. Okay, so another way to think about this is we had an overall increase of 18-to-1 in speed. And that should match up with if we do a gear train calculation, or train value. Okay, so train value. Okay, so the driving teeth, we have, here's our first driver, 72 teeth. It's driving this 16-tooth pinion. Here's our second driver, has 80 teeth, and it's driving a 20-tooth pinion. So that should give us 18, and that's our train value. You'll notice that this is our overall train value. It was broken up into 2 stages. So we can call, if this is our input, we probably call this stage 1, and this stage 2. But pretty arbitrary terminology. I want you to maybe pause the KQ and do a little reading and see if you can determine what is the maximum train value that can be accomplished in a single gear stage. So it's not good practice to have more than a certain train value in a single stage. So that's what I'm asking you to see if you can figure out. There are limits. So for larger gear trains, what configuration is needed?